Bismillahirrahmanirrahim. Dear students, have a nice day. Hope you will be fine and best of your health. This is Dr. Sajid Mahmood Rao, Division of Science and Technology, University of Education, Lahore. Today we are talking about electrophilic aromatic substitution reactions, its synthetic applications, and key mechanism. This is our second lectures on this topic. The key concept of today's class session is electrophilic aromatic substitution reactions, key mechanisms, synthetic applications of the organic compounds. Today we will discuss the bromination of benzene. Let's see what is bromination. Bromination fall in halogenations, which is an example of electrophilic aromatic substitution. In electrophilic aromatic substitutions, a benzene is attacked by an electrophile, which results in substitutions of hydrogens. However, halogens are not electrophilic enough to break the aromaticity of benzene molecule, which require a catalyst to activate it. Hence, halogens need the help and aid of Lewis acids catalysts to activate it to become a very strong electrophile. Examples of these activated halogens are ferric halides, aluminum halides, where we use bromine and chlorine. In the example of bromination, in order to make bromine electrophilic enough to react with benzene, we use the aid of an aluminum halide such as aluminum bromide. So, in the statement of bromination, the introducing of a bromine as an electrophile to the benzene molecule by replacement of the proton in the presence of Lewis acid such as iron tribromide referred to as bromination. In the example, you can see over here when the benzene molecule is treated with bromine in the presence of Lewis acid that activated, and that is iron tribromide, we get the final substituted product, that is bromobenzene, by the formations of side product, that is acid bromide. So halogenations or the brominations is carried out in the presence of Lewis acids because it activates the reactions. So have a look on the important key points of the bromination. Bromine itself is insufficient electrophile to react with benzene. Therefore, it is very difficult to generate bromine as an electrophile. So, a strong Lewis acid such as FeBr3 is used as catalyst. FeBr3 forms a sigma complex with bromine molecule that reacts with like bromide as an electrophile in the mechanism. Bromine donates a pair of electrons to form a strong electrophile, that is bromine as a cation. Attack of pi electrons on bromine iron tribromide complex to form a sigma complex. Iron tetrabromide acts as a weak base to remove a proton from sigma complex and regains aromaticity. Hydrogen bromide is produced as a byproduct, and iron tribromide is worked as catalyst, which is regenerated at the end of the reaction. Finally, aromatic product, that is bromobenzene, is synthesized. So here one thing is important: if we cannot use the catalyst, that is iron tribromide, the reaction of bromine with benzene molecule is difficult and it cannot be proceeded for enough production yield. The key mechanism of bromination consists of the following three steps, that is formations of a strong electrophile. The second step is electrophilic attack and formation of the sigma complex, and third step is loss of a proton, which gives the final product and regains the aromaticity. Let's see all the steps in details. With iron bromide as a Lewis acid, we can mix bromine with iron tribromide to give us bromine as an electrophile. The presence of bromine as an electrophile is a much better electrophile than the bromine alone. Bromination is achieved with the help of iron tribromide, that is Lewis acid, as it polarizes the bromine-bromine bond. The polarization causes the bromine atoms within the bromine-bromine bond to become more electrophilic. The presence of bromine as a cation compared to the bromine molecule alone is a much better electrophile that can then react with the benzene. In the first step, the lone pair of electrons of the bromine molecule is attacked on the iron atom of the iron tribromide, which is electron deficient as compared to the previous one. So in this way, a strong electrophilic intermediate is generated here. As the bromine has now become more electrophilic after the activations of a catalyst, an electrophilic attack by the benzene occurs at the terminal bromine of bromine iron tribromide complex. This allows the other bromine atom to leave with the iron tribromide as a good leaving group, as iron tetrabromide. Here, a sigma complex is generated which stabilizes itself through resonance phenomena. In the last step, after the electrophilic attack of bromide to the benzene, the hydrogen on the same carbon as bromine substitutes the carbocation in which resulted from the attack, hence it being an electrophilic aromatic substitution. Since the byproduct, that is iron tetrabromide, is a strong nucleophile, it pulls off a proton from the hydrogens on the same carbon as bromine. In the end, iron tribromide is not consumed by the reaction and is regenerated because it serves as our catalyst in the halogenation of benzene. In this way, we get the final substituted product, that is bromobenzene. Let's see the energy profile diagram of bromination. In the energy profile diagram, as you can see over here, we have energy in the y-axis and reaction coordinate, that is time, in the x-axis. Initially, when the benzene molecule is treated with bromine in the presence of iron tribromide, we required minus 10.8 kilocalorie per mole energy, because at this stage the reaction is endothermic and maximum energy is required to start the reaction. So this reaction, that is called the first step, is generally known as rate limiting step as well as slow step mechanism. When the energy reached at the maximum value, at this we observe the transition state, because here the formations and the breaking of the bond takes place simultaneously. When the intermediate is generated, then the energy is decreased and we get electron deficient carbon benzene molecule obtained. After that, when again the attack of the nucleophile to abstract the protons from the electron deficient carbon atom takes place, then a much higher energy is required. Again, energy is increased, as you can hear in between the two values. After that, when the final product is produced, that is takes place under exothermic reactions and we get the final product, and here minimum energy is required for the formations of the final product. Let's see the application of bromobenzene. Bromobenzene is used to introduce a phenyl group via platinum catalyzed coupling reactions such as Suzuki reactions. Bromobenzenes can be used to prepare the corresponding Grignard reagents, that is phenyl magnesium bromide. Bromobenzene is used as a precursor in the manufacture of phenyl cyclidene. Bromobenzene is a heavy colorless liquid with a pungent odor and is also known as monobromobenzene and phenyl bromide. Bromobenzene is used as an additive to motor oils, as a crystallizing solvent, and in the productions of the synthetic intermediate phenyl magnesium bromide. The sigma bond between the bromine and benzene carbon allows for inductive withdrawal of the electron density from the benzene ring. Hence, bromobenzene typically reacts slower than the benzene molecule. Bromobenzene is an aryl halide which can be formed by the electrophilic aromatic substitutions of the benzene using bromine. It is a clear, colorless, and pale yellow liquid. It is soluble in methanol and diethyl ether and very slightly soluble in cold water. It is flammable, insoluble in water. Bromobenzene may be sensitive to light. Chlorination of benzene. Let's see the statement of chlorination. The introducing of chlorine as an electrophile to the benzene molecule by the replacement of the proton in the presence of Lewis acid, that is aluminum trichloride, which activates the reaction rate, referred to as chlorination. In the example you can see over here, there is a reaction carried out between benzene molecule and chlorine in the presence of iron trichloride, which is Lewis acid, and act as a catalyst which activate the reaction rate. So we can get the final product, that is chlorobenzene, by the formations of the byproduct, that is hydrochloric acid. You can observe here there is a substitution takes place between the terminal proton of the benzene molecule and the chlorine atom in the presence of Lewis acid. Let's see the important key points before developed and the key mechanism of the chlorination. As you know, the chlorine itself is insufficient electrophile to react with benzene like that of bromine. Therefore, it is very difficult to generate chlorine electrophile. A strong Lewis acid such as aluminum trichloride is used as a catalyst. Aluminum trichloride forms complex with chlorine that reacts much like chlorine electrophile. Chlorine donates a pair of electrons to form a strong electrophile in the form of chlorine electrophile. Attack of pi electrons on chlorine aluminum trichloride complex to form a sigma complex, that is our first intermediate. Aluminum tetrachloride acts as a weak base to remove a proton from sigma complex and regains the aromaticity. Hydrochloric acid is produced as a byproduct, and aluminum trichloride is worked as catalyst, which is regenerated at the end of reaction. Finally, the aromatic product, that is chlorobenzene, is synthesized. The key mechanism of chlorination consists of the following three steps. In the first step, the formations of the electrophile takes place. In the second step, the attack of pi electrons of the benzene molecule to the electrophile and produce the sigma complex. In third step, deprotonations of from the benzene molecule to gives the final product. Let's see the each step in details. In the first step, the chlorine molecule behaves as a Lewis base and it donates a lone pair of electrons to the ferrochloride, which is a Lewis acid. In this way, a molecular complex with a positive charge on chlorine is generated, that is our first intermediate, which is resolved into an ion pair containing a chlorine ion, that is chlorine as an electrophile, and iron tetrachloride, which will behave as a base, and the final step. In the second step, the pi electrons of the benzene molecule attack on the chlorine, which is a strong electrophile. This is slow step and also known as rate determining step. Here, there is a stabilized cation intermediate. The positive charge is delocalized onto three atoms of the ring, which is generally known as sigma complex, and it stabilizes itself through resonance phenomena. In the final step, the aluminum tetrachloride, which behaves as a base, it abstracts the protons from the electron deficient carbon benzene. Uh, in this way, the sigma bond which once formed between the protons and the carbon shift back towards electron deficient carbon atom of the benzene and regains the aromaticity by the regenerations of aluminum trichloride and hydrochloric acid. In this way, the final product, that is chlorobenzene, is synthesized and aluminum trichloride is again produced here, which is regenerated and worked as a catalyst. Application of chlorobenzene. The major use of chlorobenzene is an intermediate in the productions of commodities such as herbicides, dyestuffs, and rubber. Chlorobenzene is also used as a high boiling solvent in the manufacturing of adhesive, paints, paint removers, polishes, dyes, and drugs. Chlorobenzene, also known as monochlorobenzene, benzene chloride, chlorobenzole, and phenyl chloride. It is also used in the productions of chloronitrobenzene and diphenyl ether, as well as in rubber intermediates. Chlorobenzene can also be used as dyeing carriers or leveling agents for dyeing, printing, and coating of textile and leather materials, including fibers, yarns, and fabrics. They may also be used as deodorizers, fumigants, degreasers, and defoliants. Chlorobenzene is applied as an antioxidant gum additive, and it is used in the manufacturing of polyaniline, a conductive polymer. In dyes industry, it is used for the indigo production. Monochlorobenzene is also an important element in the productions of API, that is active pharmaceutical ingredients, which are used for the taste masking and to give the shape, and also used as a preservatives in the pharmaceutical dosage form. Nitration of benzene. Let's see the statement of this reaction. The introducing of nitronium ion as an electrophile to the benzene molecule by the replacement of the proton in the presence of a mixture of hot concentrated nitric acid and concentrated sulfuric acid at low temperature, with the most safer and convenient method referred to as nitration. As you see in the example, the reaction of benzene molecule is carried out between nitric acid and sulfuric acid, and we get the final product, that is nitrobenzene. The reaction is carried out in the presence of sulfuric acid because when we use simple nitric acid, the reactions might be explode. Therefore, a safer and convenient method is used with the help of sulfuric acid that behaves as a strong base and gives its proton to the nitric acid. In this way, nitric acid becomes protonated to facilitate the reaction mechanism. Let's see the important key points which are definitely would be helpful to develop the key mechanism of the nitration of benzene molecule. The simple reaction of benzene with hot nitric acid is not so easy because hot nitric acid and benzene give sluggish reactions and might be explode. Therefore, a safer and more convenient method is used by the mixture of hot concentrated nitric acid and concentrated sulfuric acid. Hence, a reaction is carried out at low temperature. Concentrated sulfuric acid is used as a catalyst, which is regenerated at the end of reaction mechanism. As a strong acid, concentrated sulfuric acid behaves as an acid, while nitric acid behaves as a base. So, concentrated sulfuric acid gives its proton to the nitric acid, and hence nitric acid is protonated, which after that leaves water molecule and convert into nitronium ion. The nitronium ion is now can be used as a strong electrophile for the nitration of the benzene molecule. Here, protonated nitric acid leaves the water molecule and generate a powerful electrophile, that is nitronium ion. The nitronium ion now can be introduced to the benzene molecule as a powerful electrophile by the replacement of the proton of the benzene ring. The nitronium ion reacts with the benzene to form a sigma complex, which stabilizes itself by the resonance phenomena. Loss of proton by the persulfate from sigma complex gives nitrobenzene, that is our target compound. The key mechanism of nitration of benzene molecule consists of the following three steps. The first step is preliminary step in which formations of the nitronium ion takes place. The second step is attack on the electrophile that forms the sigma complex. Third step is loss of proton to give the nitrobenzene. Let's see the details of these steps. In the first step, nitric acid has a hydroxyl group that can become protonated and leave as a water, similar to that of dehydration of an alcohol. Here we use two acids, nitric acid and sulfuric acid. Sulfuric acid, because it is a strong acid, therefore it behaves as an acid, and the nitric acid behaves as a base. So sulfuric acid gives its proton to the nitric acid. In this way, nitric acid becomes protonated and we get the first intermediate, that is protonated nitric acid. The protonated nitric acid leaves a water molecule and we get the first nitronium ion, that is a powerful electrophile, and that can be introduced easily to the benzene molecule by the replacement of the proton. Here you can observe the formations of the water molecules and the persulfate. The persulfate will be used at the end of the reaction mechanism for deprotonation purpose. In the second step, the pi electrons of the benzene molecule, as you know, behaves as a nucleophile. It attacks on the nitronium ion, in which the nitrogen atom is electron deficient, and become a new bond, that is sigma bond. This new sigma bond is called the sigma complex or an adenine ion, which stabilizes itself by resonance phenomena. In the last step, the persulfate attracts the proton from the electron deficient benzene molecule. In this way, it produces sulfuric acid, and the sigma bond which once formed between the carbon and the protons of the benzene shift back towards electron deficient carbon of the benzene. In this way, the aromaticity of the benzene molecule is regenerated. Sulfuric acid here is regenerated and is used as a catalyst. Applications of nitrobenzene. As you know, the nitrobenzene have synthetic and rich applications due to the presence of nitrogen atom within the molecule. Because nitrogen atom is very active entry of this molecule. Nitrobenzene is used to produce lubricating oils, which are used in the motors and machinery. A small amount of nitrobenzene is used in the manufacture of dyes, drugs, pesticides, and synthetic rubber. Nitro compounds undergo tautomerism in solution to azinitro which is acidic in nature. Hence, all the nitro compounds are weakly acidic in nature. They dissolve in bases to give salts and can be regenerated by adding a strong acid like hydrochloric acid. In the pharmaceutical industries, nitrobenzene is used in the productions of the analgesic drug, acetaminophen drug, or paracetamol. All these drugs are used to remove the body temperatures or to lower the body temperatures in pyrexia condition. Nitrobenzene is also used in shoe and floor polishes, leather dressings, and paint solvents to mask unpleasant odors. In textile, sodium metanitrobenzene sulfonate, often referred to by the brand name that is Lidigol, which have been launched to the market. This chemical is a mild oxidizing agent that is sometimes used to protect dyes from degradation caused by reducing conditions that exist at high pH and high temperature, especially where air is excluded from the dyeing vessels. In fertilizers, there is increasing use of this compound as plant growth nutrient in recent era because it promotes flowering in plants and also prevent flower from shedding. Nitrobenzene is a combination of nitrogen and plant growth regulators that act as plant energy energizer, flowering stimulant, and yield booster. Sulfonation of benzene molecule. Let's see its statement. The preparation of benzene sulfonic acid by introducing of sulfur trioxide to the benzene molecule in the presence of a solution of 7% sulfur trioxide and sulfuric acid referred to as sulfonation. In the example you can see over here, the reaction of benzene molecule with sulfur trioxide is carried out in the presence of sulfuric acid. Sulfur trioxide here is a powerful electrophile because there is a presence of 3 oxygen atoms within the sulfur, which make it more electron deficient and make a powerful electrophile. So the attack of the pi electrons upon the sulfur trioxide is easier. In this way, a new bond is formed between the sulfur trioxide and the carbon atom of the benzene molecule. Finally, we get the benzene sulfonic acid, that is 95% in the product side. These are the key points which are helpful to design the key mechanism of sulfonation. Fuming sulfuric acid is used in this reaction mixture. A solution of 7% sulfur trioxide and concentrated sulfuric acid is the common name of fuming sulfuric acid. Sulfur trioxide is the anhydride of sulfuric acid. So the addition of water to sulfur trioxide gives the fuming sulfuric acid moiety. Sulfur trioxide is uncharged. However, it is a strong electrophile with 3 sulfonyl bonds. These oxygen atoms with the sulfur trioxide makes it powerful electrophile by withdrawing electron density away from the sulfur atom. In this way, the sulfur atom becomes electron deficient, so the attack of the pi electrons of the benzene molecule easier to the sulfur atom. Pi electrons of benzene attacks on sulfur trioxide, forming a sigma complex. Loss of protons on the tetrahedral carbon and reprotonation of oxygen gives benzene sulfonic acid, that is our target compound. The key mechanism of sulfonation consists of 3 steps. The first step is attack on the electrophile, forms the sigma complex. Second step is loss of proton that regenerates an aromatic ring. And third step is the protonation of sulfonate group upon the benzene molecule by a strong acid. Let's see the details of each step. As you know, the sulfur trioxide is a powerful electrophile. So in the first step, the pi electrons of the benzene molecule that work as a strong nucleophile attack on the sulfur atom of the sulfur trioxide molecule. Here, sulfur atom becomes more electron deficient due to the presence of oxygen atom because oxygen atom withdraw all the electrons from the sulfur atom. In this way, sulfur trioxide becomes a powerful electrophile which can be introduced to the benzene molecule by the replacement of the protons of this ring. So in this way we can obtain a sigma complex that can itself stabilize by the resonance phenomena. In the second step, the persulfate, which behaves as a base, it deprotonates the proton from the electron deficient carbon atoms of the benzene molecule, that is called sigma complex. In this way, the sulfuric acid is regenerated here, which works as catalyst, and we can obtain a benzene sulfonate anion. In third step, the sulfonate group of the benzene molecule may become protonated by using a strong acid. In this way, we obtain the target compound, that is benzene sulfonic acid. Let's see the applications of benzene sulfonic acid. Benzene sulfonic acid and its salts are used as detergents, as degreasers, and in meat cutting rooms. It is also used as a laboratory chemical to make detergents and in electronically cleaning and pickling bath. In pharmaceutical sectors, it is used as an inactive ingredient that is called active pharmaceutical drugs. In the pharmaceuticals industry, it is used as antimicrobial preservatives, antifungal agents, and tablet and capsule lubricant. Benzene sulfonic acid has been used in the combination with salicylic acid as in Whitefield's ointment for the use as antifungal for athlete's foot and ringworm. In textile, benzene sulfonic acid is used in hair shampoo, bath shampoo, dish detergents, and complex soap, laundry powders, dishware cleaners in daily chemical industrial. Benzene sulfonic acid is used in wetting and clear dyeing assistant in the textile industry too. Benzene sulfonic acid is commonly used as the active ingredients in the laundry as well as in clothing washing machines. Benzene sulfonic acid is often used to convert to other specialty chemicals which can be used in the organic synthesis. Desulfonation of benzene. Sulfonation is reversible and a sulfonic acid group may be removed from an aromatic ring by heating in dilute sulfuric acid, generally called as desulfonation. In practice, steam is often used as a source of both water and heat for desulfonation. You can see over here in the example, the benzene sulfonic acid is treated with dilute sulfuric acid. In the presence of a mild heating, we can obtain again the benzene molecule, that is 95%, by the removal of sulfuric acid as a byproduct. Dear student, this is your assignment and quiz. The first assignment is that paraxylene undergoes nitration much faster than benzene. Use resonance forms of the sigma complex to explain this accelerated rate. The second assignment, use resonance forms to show that the dipolar sigma complex shown in the sulfonation of benzene has its positive charge delocalized over 3 carbon atoms and its negative charge delocalized over the 3 oxygen atoms. The third assignment, step 2 of iodination of benzene shows water acting as a base and removing a proton from the sigma complex. We did not consider the possibility of water acting as a nucleophile and acting the carbocations, as in an electrophilic addition to an alkene. Draw the reaction that would occur if water reacted as a nucleophile and added to the carbocation. Explain why this type of addition is rarely observed. In the next topic, we will discuss the Friedel-Crafts alkylation, Friedel-Crafts acylation, its applications and comparative study. Thank you.